Hi. Yes, I think everything is ready. So hi, I'm back. Sorry for being away for 2 weeks. Anyway, I'm trying to catch up and post all the lectures, homework, and hopefully I'm gonna hear this office hours, which is a discussion on the topic for the previous week, plus some maybe problem solving together. So anyway, let's get back to what we are left. So last week was lecture 12. Oh, actually, by the way, I think I'm missing the lecture number. Like, this is supposed to be week 13 or something. But like, I got a call and it said it's supposed to be week 11. But yeah. And anyway, I'm gonna make sure I have all the lectures before the finals. So final is going to take place. I forgot. Mid-May, I think it's something like 11 or 10. Let me check the calendar real quick. I think I set it to be May 8 or 15. Yeah, so about like 3 weeks from now. And of course, we are having online exams. And since I can't just like I'm trying to like read and study how to properly holding like a class online, and I'm not satisfied with the way people try to like have the same format for the exam. And they force you to like, have a camera on like your paper, and then you have to work for 10 or 15 minutes, and it has to be the speed test because otherwise someone can like finish all the exams and give that copy to everyone else. So nothing makes sense. So what I'm trying to do is like have a mix of two formats. First, it's going to be the take home exams. So I'm just gonna release the exam for everyone, and you have a day to finish it on your own, open book. So take your time and finish that in a day. I will try to have it be about an hour or 2 hours exam, including like searching things online. So that's one part. The other part is I don't know. I don't want it to be just purely take home exam. So the other part may be just quick short question. I ask you to do something and then you answer by describing or writing something real quick, which should take at most 15 minutes each person. But I will give you the exact details on how the exams is going to work by, I don't know, before a week at least before the exam. And so let's not be worried about that yet. So let's get back to the class and we just talk about the it's flipped, by the way. Yeah, the confidence interval. Okay. So let's recap what we have learned last week. So we talk about the normal distribution. Right, I hope you haven't forgotten about it yet. The thing we have like this curve, and I mean this the graph, the x and y axis, and we have the bell curve. The normal distribution with some mean mu and some standard and some variance sigma. Sorry, some standard deviation sigma. Right. We have defined that somehow, like, and we justify that we define this way because that agrees with this theorem. Right. The central limit theorem guarantees that the average of whatever we are trying to compute is going to be normally distributed. So even if like if you remember the image, like for like any kind of distribution, you may have a triangle, you may have just the standard, the uniform distribution, or you may have anything fancy the exponential. Right? If you take the mean, the average, then everything is gonna give you the bell curve, and that's how we define the bell curve in the first place. So that guarantees us, okay, whatever we have at first, if we talk about the numbers, the center or the spread, then that number is gonna follow the standard, the normal distribution. That's the standard form. And then finally, we talk briefly about the C table. Right? For the old school, you have to look up the whole table and pick the value you want to compute. But nowadays, use any app or the website I gave you last time to just type it in and get the result immediately without having to like be frustrated whether you get the right one in the row, in the column. Right. So that's the main things we talked about last time. We talked about more on the theory side. Right, we have all this stuff, all these maths fancy tools. So today we are going to talk about how to use these two in the I don't want to use it in the real world because it's not that real. It's real if you are a statistician, but if you are just a math people or just any normal person that just want to get a glimpse of how statistics works, then it should be enough. So let's dive into the application. Right, so the first section is about the estimation, because of course we want to estimate things, right? In statistics, you are not going to get the exact number. You're not going to get the exact mean, the exact variance, the exact standard deviations, or whatever number they are. So you're going to estimate. But before we go all the way there, I think the camera, okay, it's just fine. So let's go back and talk about the two branches of statistics. In the first half of this class, I hope you learned the descriptive statistics. Right, I think it's the first 2 weeks. Right, let's just discuss how you can represent graph in the nice ways. Pie chart, whatever chart. You get the numbers. Let's just say you have a spreadsheet of all the data, and you want to turn that into something that people can easily digest, not just the numbers in the table. So you get all those graphs. Right? That's what we call the descriptive statistics. And then we have another branch, which is called the inferential statistics, which is what we are studying right now. So we take those numbers and turn that into something more meaningful. And we are going to discuss on what it means to be meaningful, right? So that's the branch. If you are working on something that's statistics, then you usually have to follow along all these graph flowchart. I mean, right? So what do we start? We start with what we call the sampling. Okay? Sampling means you get some information, right? Whether it's a raw information, it's a questionnaire, it's a poll, it's something you generate by using an app or whatever. You get a sample. You get a set of samples. Right? So from that point, you first start with trying to turn that into something that is visual. And you can think about all the charts. Right? We have two different ways. We have the graphs, all the nice graphs that you can use. I think spreadsheet, words, all the tools. Just pick your favorite, or just pick one that suits your set of data. And the other one we compute kind of these two properties, or I think we call it parameters of the set of samples. Right? If we plot that into the bar graph or plot all of them into a line, then we want to look at where the center of the data is, right? Or where the average it lies, and we want to look at the spread. Right? If it's widespread, everything is equally likely, or if it's centered around just a small range, small interval of numbers. So these are two main attributes, right? And from that number, from the mean mu and from the standard deviation sigma, then we are using what we call the second branch, right? The statistical inference. From that number, what can we say about them? What can we say about the sample itself? But before we can systematically, we can mathematically get some meaningful result, then we have to go back and study some probability. Not some, like 2-3 weeks, right? So we want some kind of theory to back up the results we are going to study. Right? We cannot just like say, okay, that's the center, so that's the center, that's spread, so that's the spread. That's all we can think. That's all we can say. No, we can say something a little bit more about the data itself if we have some math background, which is why we go back and study probability for a bit. Now, once we have these two information, we have the measurements, the data from the sample, and we have some mathematical theory. Then we can combine them and say something about the set of samples. And this is where we are at right now. We can say two things. They are like actually the same thing, but just make them two branches. So we can estimate something, right? So maybe from that, let's say we have a sample size of 30 or something. We know the center, the average is about 15. You know the standard deviation is 0.5. Right? We are trying to deduce what else can we say about all these numbers. We may not need to get every single sample. We just need these main attributes, these main parameters to compute something else. And from these things, what can we estimate something? Can we say more about that set of data? And from that point, actually, it should be an arrow here too, because I to understand that the last topic, we need to understand how we estimate stuff. Right. So after we get a good estimation of something, now then we can finally make an informed decision. Because statistical, mathematical decision, right? From all these numbers, like if let's say you want to buy a house, get some set of data, right? At the end, you want to be able to decide for yourself if you should buy this thing or not, if you should buy this thing or another. And once we have computed everything and get one synchronized number, then we can make a decision based on that number. But if we don't, like you may notice that that's kind of like a long way until we can get to the final decision making here. In the reality, that's all. This should be like familiar to all of you. Okay, so we get a sales sample. Let's say you, I don't know, take 10. You go to 10 restaurants, right? And from your judgment, you conclude that they all suck or something. I don't know. But like you from the set of sample you have, right? You use your brain, right? You use your feeling, or gut feeling or whatever, and you come up with the conclusion to do something or not to not do something. Okay. This is kind of, as you can see, they are all blur into the background, into the abyss. So if you don't have this kind of background in statistics, right, you want to be able to make nice decision based on numbers, of course. But just as a note, like this is intuitive, like because we are human, and human just use your brains. You don't need calculator to decide if you want to get vanilla or chocolate ice cream today. Right? But for more sophisticated, for more complex problems, then you need a rigorous procedure. You need an algorithm that guarantees you a number or something that you can look and understand and conclude something in the end, which is what we are trying to get, right? Or if you like some meme, I don't know what kind of meme this is called, but like instead of like going all through all these like processes, you may just decide on whatever you want to from looking at the data. Right? So if you don't want to drift, like make a shortcut, then you have to like understand how you can go from the raw data to something else that is more meaningful. And that the thing that is meaningful is that thing also matters, right? Because maybe you want to buy a house and you have to like actually get some reasonable set of estimates or data to decide if you should buy it or not. So by the way, if to describe this process in a more compact way, you can think of it as a gambling. Right? You see the cards, you compute something in your head, and you decide whether you should play this game or not in the first place. Or if you play this game, you should decide if you should bet on something, if you should change your cards or whatever. That also applies here. In theory, sometimes it only goes from the sample. Oh, sorry. In math, if it's about cards or coins or dice or whatever that you can just simply compute, then you can go straight from probability to that. We don't having to deal about to deal with the samples, because you don't have samples in the first place. You have a deck of cards, and you know exactly what cards are there. You know exactly what distribution they are. So you don't have to go back one step. So let's get to sampling. Just for the note, sampling means you have a population, like a large one. Let's think of these dots as people. Right? Then you want to sample. You want to pick people at random, maybe 20, 10, 13. How many you want? Right. And the question is, from this one, right, from this set of sample, what can we say about the data itself? Right, so let's I think we swapped the slides a little bit, but anyway, so let's first start with the definition. So we have two scenarios. We have the population itself, right, that we are trying to get some meaningful information from it, and we have a small sample that we get from randomly picking stuff from the population. So we have some parameters on one side, and we have different parameters on the other side. So the way we are going to call these two parameters with different notations. So for example, we have three main parameters, right? We have the mean, the average that we all use and apply anywhere, right? We have the sample parameter. That means this x bar, like this notation, is the mean for the sample. Well, actually, I should like repeat that. We have up. That should be here instead. I can't flip this. So like we have a big population. Let's just put something at random, and we pick a sample. Say 10 people or 10 balls or 10 whatever. Then from this sample we can compute our three main parameters. Actually two, but in this case we are gonna add one more. We can compute the mean, the average of whatever we got from the sample on the left hand side. We can compute the proportion or the ratio or the density of the small sample, and we can compute the variance. Right, if you remember that something is like the difference square divided by the size of sample itself. This variance that measure how spread is set of samples. These three numbers are the things that we can compute, the things that we get from this set. Because we have only small sample size, and we can just manually compute and manually add them up and divide it by the size to get the average. We can manually count how many stuff we are interested in and divide it by the size. We can compute the variance again. But the main question or the main problem is we actually want to know these things. We want to know things on the right hand side. We want to know the mean, the average of the whole population, right, of this large box, or of 1 million people in a province or a country. We want to know again the proportion. We want to know the variance. Right? These three variables, I should call it that. These three are hidden in the sense that there is no way you can get the exact number. Like the number is there. Like if you actually have time and have money and have whatever to go to ask every single person in the universe, right, you are going to get that three numbers, that exact number. But in practice, it's not going to happen. Right? But we want to get these numbers anyway. And since we cannot get the exact number, then our best job is to estimate it. To estimate the exact or the hidden population parameter using these three sample parameters that we get from the small sample size. We get the x bar from this, and we want to estimate the actual population mean. We get the proportion from this small sample size, and we want to estimate the actual population parameter. We get the variance from the sample. We want to use that to estimate the actual population parameter for the variance. So this is the question and what we are going to learn today. And just a quick note, why on the right hand side, right, these three numbers are fixed, like unless people die or whatever. We say that they are objects, and there must be like a mean or a proportion or a variance for those objects. Like the number is there, like it's constant. But for the sample, these three numbers on the right hand side, these things change from one experiment to another. If you do the sample today, you may get these three numbers. Like if you repeat the same experiment, or if we get a different set of samples, then we are going to get the different set of parameters anyway. Right, so these three is gonna change. Right, we cannot guarantee anything about these three numbers, but we are trying our best to use these three numbers, these three parameters on the left hand side to estimate those on the right hand side. So let's say, for example, that we usually in statistics we usually use balls because it's easy to visualize. Like we have balls, red balls, green balls, and you put balls in those bags and you pick the balls out. So let's replace that by Pokeballs. And let's say you have a bag containing 30 Master Balls. I hope I don't mispronounce any of those words. And 7 normal balls. And for those of you who haven't played any Pokemon games, Master Balls are better balls. It's not normal, it's better. And anyway, you have a higher chance to catch a Pokemon if you use a Master Ball. So anyway, from this bag, there are the total. There's a total of 100 balls. 30 of those are Master, and the rest 70 are normals. Right? You take 10 balls from that bag at random without replacement. That means you take 10, place them outside. You don't take and put back. You just take them outside, and you see 4 Master Balls. So the question is, determine the population parameter for proportion P and the sample parameter for proportion P hat. Oh, by the way, yeah, that's a hat. I don't know why they use hat. Okay. So from this simple experiment, or sample, we want to get these two numbers. Just to give you an idea of what these things are. So let's recall that the population means when you think about population, you think about the large size, the large set, right? So which one is larger? You can just simply see that okay, the bag is larger because the bag has 100 balls. Right? So the population parameter for P for the bag, right, is the number of things we are interested in, right, divided by the size, the number of things in total. So there are 100 balls in total. I think, oh, let's change a little bit, right? And there are only 30 Master Balls, right? So that's 30 over 100, or simply 0.3. Right? The proportion of Master Balls in the bag is 0.3. On the other hand, right, just for the sample from all these 10 balls we have here, right, you can count how many are there, but we are going to have to use the different sets. We don't use the bag, we use what we have here. What we have here is we see the total of 4 Master Balls out of 10 balls. And so that's 4 over 10. So the number is 0.4. And it's as simple as that. But just to give you an idea of how these two numbers can be different depending on how well or the way you take samples of this bag. And so that's simple enough. So the question here is, like, if we see 4 Master Balls, what can we say about the proportion of Master Balls, or the ratio of Master Balls inside the bag itself? And because we don't know, we know that there are lots of balls in that, and we can take only 10 at a time. So how can we say about, how can we use this information, this just 10 balls, to deduce something, to infer something about the bag itself? So let's go back. Let's go back to the experiment. You take 10 balls from the bag. Let's say we know nothing about the bag itself. Oh, sorry. Let's suppose that the bag has 10 balls. We know that we know there are 10 balls, but we don't know how many of them are Pokeballs or how many of them are normal balls. So what can we do here? So we can just say we can take all 10 balls, right? Because the goal is to say something about the bag, right? We can, of course, we can take all 10 balls and look at them and count them all, right? If you take all of them, you are guaranteed that you can, let's see, you are guaranteed to get the exact P, the proportion of master balls or of all the balls. Okay. If instead we only take, I'm sorry, what if we take only 9 balls? And then suppose that we see, I think 3 master balls. What can we say about the bag itself? That's supposed to be right. Let's visualize this. We take 9 balls. 1, 2, 3, 4, 5, 6, 7, 8, 9, and we know that 3 of them, maybe this one, and this one, are master balls. Right. Since there are 10 balls in the bag, we don't see the content. We don't see the last ball that is now at the bottom of the bag, right? So that ball can be either the master ball or the normal ball, right? We don't know. So the best we can say is, the best we can infer is that there are 3 or 4 master balls. Right? It should be simple enough, right? We only see 9 balls. We don't see the last ball, the last thing. Right? Since the last thing, if the last ball is a normal ball, then this bag contains only 3 master balls. If the last ball is the master ball, then this bag contains 4 balls. So it's either 3 or 4. And we will never know unless we get that last ball out of the bag. Right, so that's the best we can say, either 3 or 4. What if we instead change the number to 5 balls? Like we take 5 balls, like we see 4 normal balls and we see 1 special master ball. What can we say about the bag? The contents of the original bag? So of course we see 1. So it's not gonna be a 0, right? This case is ruled out because we see now, we see at least 1 now. So that's all. Is it possible to have 1 ball in the bag? I mean 1 master ball. 1 master ball, sorry, in the bag. Of course, it is possible. Like if all the 5 balls, the rest of the bag, are all normal balls, then that's gonna be just 1 single master ball. Right? And if you want to compute the proportion, the ratio is going to be 0.1, like 1 over 10. Is it possible to have 2 master balls? Of course, yes, because like if out of those 5 hidden balls in the bag, if exactly one of them is a master ball, then this bag contains exactly 2 master balls. Then yes, this is also possible. What about 3? Right, 3 is again still possible. 4? Yeah, sure. Like we can have 3 here, so that it adds up to 4 balls. What about 5? Sure. 6? Yes. What about 7? Can there be 7 master balls in this bag? And if you, yeah, of course not, because like there are only like 5 balls left in the bag. Like even if like all of them, every single ball in the bag are all master balls, then the total would be 5, right, plus 1. So the maximum is 6, and you cannot get 6 balls. You cannot get 6 master balls in the bag that contains 5 balls. Right, that doesn't make sense. So like even if like the whole bag, the rest of the bag are all master balls, then the total number is at most 6. So now what we can say about this bag? We can say that okay, contains 1, 2, 3, 4, 5 or 6 balls. Nice. No more, no less. It's between 1 to 6. It's not gonna be a half. Let's say that the number is integer. So that's all you can say about this bag. 1 to 6. If you use some more math notation, you can use this interval 1 to 6. Like that's to condense. That you don't have to write every single one. You can just write the start and the end, and put some bracket inside. And so now we know that the number of balls is between 1 to 6, which means the actual proportion P is between 0.1 and 0.6. If there is 1 ball, then the proportion is 0.1. If there are 2 balls, 2 master balls, then the proportion is 0.2, and 3, and 4, and 5, and 6, and so on. So now we narrow down, right, that P. We even if we don't see the rest, right, we can narrow down that to a smaller set of possibilities. In this case, only 6 possible cases. Can we say more about that? Like we know it's between 1 to 6. What can we say anything more about that? Suppose we don't know anything about this bag. Right? You may think, let's say, okay, if the probability that a random ball is master ball is 0.5, and you can think of this like flipping a coin. If you get a head, you get the master ball. If you get a tail, you get the normal ball. Let's say it's 0.5, right? Then there's like 0.5 chance for this to be the master ball. Like it's 0.5 chance for each. Right? So you can see that if the proportion or the probability is exactly 0.5, then it is less likely that you're gonna get all normal balls. Right? If it's actually 50-50, then you can see that okay, I believe that some of these balls, at least one of these balls, has to be a normal ball, and also on the other hand, it is not likely. It is less likely to happen. Again, if it is also less likely for all the balls, all the 5 balls to be master balls. Okay. So that means if we believe, if we are confident that these 2 cases should not happen, then we can actually narrow it down to 2 to 5. Right? We can, instead of listing all possibilities, we can narrow it down a little bit, right? But with some added condition that we are confident it is very likely that number is going to be between 2 and 5 balls. It's not going to be the extreme cases of 0, like no balls at all, or all balls, or 5 master balls. So in this case, in the first case, we can say exactly, we can just say that mathematically that P is between 0.01 and 0.06, because that's math. That's all the possibilities. But on the other hand, on the right side, we can say something right here, right, with some added condition that we think it's likely to be this small. So in a sense, this is a trade-off. We trade the accuracy for practicality. If in in the real world, if there are like 10,000 balls, and you say, okay, I believe that, or let's just use the real world. If there are like 10 million people in Bangkok, then I can say I am 100% sure that there are between 0 and 10 million female. I'm pretty sure that there are between 0 and 10 million males, right? I can say that like with 100% confidence, but that's not gonna be useful, right? Because of course it's true, it's mathematically true. So on the other hand, this is true, but not useful. Right? It's true, yeah, but it's not that useful because the range is large. On the other hand, this one on the right hand side, I narrow it down. I decrease the size of the range. So I might say there are around 4 to 6 million male in Bangkok. That sounds more like useful, right? To compute whatever you want to. Okay. So this is let me say like it is less true. Oh, sorry, this is less true. I mean it's still true, but sometimes we have like a tiny chance to be wrong. So it's not less true. It's not. Oh, let me use this word here. I'm trying to say that it is not always true, but nevertheless, this is more useful. Right. So now we can use like base our decision on that information we got from our computation. Okay. So these are the trade-offs that we have to choose. Do you want to be confident? Do you want to be true 100% of the time, but get some information that is not, that is like maybe it's trivial. Like if everyone knows it's between 0 and 100 or 0 and 1. Okay. Or on the other hand, you can use some math. You can plot the graph, compute something, get some numbers, and narrow it down to a small range that you can actually use to make some informed decision for yourself. Right. So this is what you have to decide for yourself. Like if you write a math paper and if you want to actually prove something for your math teacher, like me, then you have to go this route. You have to make choice 100% sure. Okay. But in practice, if you are the statistician, if you just want something useful that you can use in real world, that you can apply to, then you are going to use this route instead. So that's the high level idea of what we are trying to accomplish. So you may ask, so why can't we just pull everything out the back, right? If we want to know the exact number, if we want to know the population parameters, then why don't we just like get every number out of that? So let's maybe pause the video and write some reasons down. Let me give you a minute. Okay, let's suppose we run back. Like, of course, if you want to know the exact number, then why can't you just do that? Of course, because it's like the short answer is not practical. It is not practical. Sometimes actually replace that by like most of the time. Like if you want to make a survey on people in Bangkok, then you are not going to be able to ask every single one of them. Right. And then there's the cost, like both time and money that you have to spend. Right, to perform a survey for 10 million people, no, that's not gonna be done in a year or 5 years, right? And that's the one. This point is kind of interesting because like, even if you have time and money and whatever to perform a survey for every single person in Bangkok, then the problem is like there are going to be errors anyway. Right? Because maybe someone put in the wrong data, someone compute something wrong, or whatever, you lose some documents. Right? Because we are human and human make mistakes. So we are going to get the exact number anyway, so why bother in the first place? So let's just get something that, okay, doesn't take too much time, doesn't cost us too much money, and get some result that is useful enough. I have this one too, but this again is kind of like the theory. So what we are oh yeah, that's one step back. So what we are trying to do is we want to use these three parameters to estimate the actual parameter. What do you mean by estimate? If let's say you get the average of 10, you can say, okay, the mu, the actual one, is also 10. You can just use that number to estimate the result. But then again, you are almost always going to be wrong. It's not going to be exactly 10. It's going to be like plus or minus some small or large amount. Right, so that you cannot just use that single number itself. You have to use some other data or other parameters to help narrow down the number or the range of possible values. So it's gonna be something like you get these three numbers, or sometimes two. It depends. You might not need all three. So let's suppose that say you get all three. Right? You're gonna put that into some kind of box, like some mathematical formula, right, and get the estimations of all the population parameters. We are going to talk about the formula in a moment, but this is what we are trying to accomplish. And the way you use it, and there is not one single formula. Right? There are many formulas. Depends on you want to get a large gap, you want to get a small gap, if you have enough information, or if you are missing something. There are all sorts of formulas. In this case, we are going to in formally we call this an estimate. It's kind of like confusing. Like we have the estimate like as a verb, and then we have the estimate as a noun. Anyway, we want to get the result. We want to get an estimation using some formula that we may be able to get from the internet, or from this class, or from wherever. And we want to talk something about the formula. We cannot just use any formula. Like for example, if I say I want to estimate the mu, I want to estimate the mean from these three, right? And okay, my formula says, you just say it's that number, but you don't change anything. Like whatever you get from the sample, whatever mean average sample you get, then you just use that as the population average. Like that's the work. Yes, it kind of works, right? But it's not practical again, because the actual number is not going to be exactly 10. Right, so we have to have like some kind of some attributes for these formulas. Like we need a good formula, of course. Like, and what do we mean by good? And these are all the words that we can like measure the formula and say whether is it good or not. So what are we looking for in an estimator? We want it to be unbiased, because if we want to have the actual number, right? And for the estimator to be unbiased, then the expected value of whatever estimator the expectation of whatever formula you have here, right? That has to be equal to the actual population parameter, because that's actually the goal. Right? We know that we are not going to get the exact mu every time, but nevertheless the number should be like between mu, like can be plus or minus. It should not be too far from mu. And in math term, in statistics term, it means the expected value or the average of those numbers, right, should be equal to the actual number itself. So what else we are looking for in a good estimator? It has to be efficient, meaning it has to be pretty small variance. Variance means the spread. It means we want that to be pretty close to the actual population parameter. And because otherwise, if we know that the number p, the proportion is between 0 and 1, we can say, okay, we can just choose one at random. Right? You can just choose one at random and use that random number as an estimate. Does that work? Yes, sometimes if you know that the average is 0.5, it works sometimes. But it is good, of course it's not, because it's not efficient. Like the variance is large. It has to be, what else? A good estimator has to be consistent. Right. Consistent, it means, again, it means close, but that means it gets closer and closer and closer once we increase the sample size to be larger and larger and larger. Maybe if the size is 30, then you get some variance. Maybe it's still large, but if you increase the size to be 100, then the variance gets smaller. If you increase the size to be 10,000, then the variance gets even smaller. So it has to be better and better as we increase the size, and it has to be sufficient. So it has to contain all the information in the data about the parameter, because this is kind of like not math term, but like, okay, if you want to estimate something, like if you want to estimate the p, the proportion, then you have to kind of like get a p from the sample, right? You cannot get just the mu, the x bar, the average, the sample average, and the sample standard deviation. You have to actually contain the information about what we are looking for. So that's okay. Okay, let's take a break and continue in the next clip.